Very pleased to have Xuding Zhu here. Maybe second time in Zhejiang. Yeah, and we'll talk about 1, 2, 3 conjecture. So 1, 2, 3, you can start.
Thanks to Niwczyk for inviting me to here, and for inviting me to hear this talk, and thank all of you to come to this talk. I came to Zhejiang, but not here. That's something like 12 years ago, 13 years ago. Yeah, so at that time there was no ideas. And now there's such a big group, so it's a wonderful place to do research. Okay, so today I'm going to talk about 1, 2, 3 conjecture. I concentrate on least version of 1, 2, 3 conjecture. So first, let's describe what is the 1, 2, 3 conjecture. So you're given a graph, and you put weights on the edges. So the weight here in this example, there is weights on the edges of 1, 2, and 3. So each edge has weight either 1, 2, or 3. Given such a weight assignment, and they define the vertex sum of each vertex to be the sum of the weights of the edges incident to that vertex. Okay. And I say this edge weighting is proper if adjacent vertices get distinct vertex sums. So like this one, this is a proper edge weighting because, say, this is adjacent, these two adjacent vertices, their vertex sum are distinct. And the only same is this one and this one has the same weight, but they are not adjacent. Okay? So this is a proper edge weighting. Okay. Now, you can so this proper edge weighting, the weights used on edges 1, 2, and 3. Okay. You can easily verify that if you just use weights 1 and 2, that's not enough. Not enough. Okay? Because if suppose you just use weight 1 and 2. This is 1. This one has to be 2 because otherwise these two vertices will have the same vertex sums. And similarly, you can find other cycle that's say 5 there again that these edges need to be have distinct edge weights. So 2 weights are not enough. Okay, so of course, if there's an isolated edge, no matter what weight you assign to that edge, the two end vertices always have the same weight, same vertex sums. So we should not allow such. We should not consider graphs which have isolated edges. So we call such graphs nice, no isolated edges. And the conjecture says that every nice graph has a proper edge weighting using weights 1, 2, and 3. And this is called a proper 3 edge weighting. 3 means that the weights used on the edges are 1, 2, and 3. So this conjecture is called 1, 2, 3 conjecture. So it's only weights 1, 2, or 3 are used on the edges. And this conjecture is very simply stated. So it's not. It does not have very long history, but it's very popular, and many people started it. So at the very beginning, when they first proposed this conjecture, they didn't know there's a constant, say 1 to 2k, so that you can find a proper k-edge weighting. But they find there's 183 real numbers. So you use real numbers instead of integers as weights, and that you can do it, get a proper edge weighting. And later on, the results, the progress on this conjecture is 30 is enough, and the 30 is improved to 16 to 13 to 5, and finally this year there's a paper put in the archive says that this conjecture is true. Okay? This conjecture is true. So this paper is just posted on archive, and we have my students and I will read it, and we think it's correct. So it's not reframed yet, but it should be correct. So this conjecture is solved. And then a related concept is total weighting. So instead of assigning weights to the edges, you can assign weight to the vertices as well. So if you have such a weighting, then the vertex sum is just the sum of the, for each vertex is sum of the edges incident to that vertex plus the weight of that vertex. And again, you want the adjacent vertices got distinct vertex sums. So then there's a 1-2 conjecture, there's a 1-2-3 conjecture, there's a 1-2 conjecture, which says that every graph has a proper 1-2 total weighting. That means you use 1 and 2, just using 1 and 2. But now, not only edges can get weight, vertices can also get weight. Okay? So even isolated edges, you don't need to be removed from the consideration because you can put different weights on the end vertices of the isolated edge. So for this conjecture, very soon after the conjecture was proposed, and Karoński proved that every graph has a proper total weighting, using weight 1, 2, 3 for edges and 1, 2 for vertices. So it's just one step away from this conjecture. But the conjecture is still open. The 1-2 conjecture is still open. 1-2-3 conjecture is solved, and the 1-2 conjecture is still open. Now, so I'm interested in the least version of this conjecture. So instead of assigning weight 1, 2, 3 to the edges, I gave each edge a list of permissible weights, a list of real numbers as weights. Okay? And they want to choose for each edge the weight from the list. And still, I want to get a proper edge weighting. Okay? And then, for example, so the edges, different edges can have different lists of permissible weights. And you want to choose one weight from its list for each edge so that the vertex sum is distinct. Then whereas the conjecture is extended to least version, 1, 2, 3 conjecture extended to least versions is every nice graph is 3 edge weight choosable, which means that if each edge has 3 choices, it doesn't matter what kind of choice you give to this edge. Provided that every edge has 3 choices, then you can find a proper edge weighting. That's 3 edge weight choosable. Then this conjecture is extended to the total version. The total version is that every graph, every nice graph is 1, 3 choosable. That means each vertex has 1 weight. That means its weight is fixed, just arbitrary. And each edge has 3 choices. Then you can still find the proper total weighting. And also there's 2 choosable. That means each vertex has 2 choices, and each edge also has 2 choices. Then again, you can find the proper total weighting for this graph. Okay, so these are some results about the edge-weighted choosability of graphs. At the very beginning, it seems that all those results about proper edge weighting using weights 1, 2, 3, and up to k, they use the property of the numbers. Right? For example, it's even or odd, modulo 4, modulo 6, so things like that. So those arguments, they cannot be applied to least version, because for the least, the number in the list for each edge is arbitrary. So we don't know what are the numbers. It could be real number, it could be integers, but it could be all odd or even. So those technicals do not apply. And these are some very early results about what are the edge weight choosability of this graph. So this means that if each edge has this many choices instead of 3, so the conjective 3, now it's 3 times delta over 2. Delta is maximum degree. And this is delta plus 1. And here each letter is an author. Okay. So finally in 2021, there's first constant Bart. And this is obtained by Chao Lu from Shandong University in Weihai. The same, though? Not the same. Okay. Yes. So every nice box wants 17 truthful. That means if each vertex is given arbitrary weight and every edge is 17 choices, then you can find a proper total weighting. In particular, every nice graph is 17 edge truthful. That means if each edge is 17 choices, but you do not give any weight to the vertex, that means each vertex weight 0, right? And then it is 17 edge choosable. And then I improved this result to prove that every nice box wants 5 choosable. So before the very last result about the 1, 2, 3 conjecture, this result matches the best result for non-least version. But now it's behind. So I hope that it will catch up again, least version, because the least version can always is behind. So the method is completely different, but it's always catch up with it. For example, we proved that every graph is 2, 3 choosable. That means if each vertex has 2 choices, each edge has 3 choices, then you can find the proper total weighting. So this matches the best result for the non-least version of total weighting. But the 1, 2, 3 conjecture is solved, but the least version 1, 2 conjecture is still open. So hopefully, I choose to give this talk here because hopefully some of you will find a way to match the non-least version of this conjecture. Okay, so now I give a sketch of the idea of the proof. So suppose let's look at this graph, and we assign to each edge a variable. Each edge is given a variable. So what is this? What is this fx? Fx is you look at this edge. Look at this edge, and you think of this each variable is the weight of this edge. Variable each you think of each variable is the weight of the edge. It's going to be replaced by some numbers. Okay? Then you look at the vertex sum of this vertex. There are 2 end vertices of x. This sum is x plus z plus w, and this sum is x plus y. Right? And if you take the difference of the vertex sum of these 2 end vertices, you got this. Say y minus z minus w is the difference of the vertex sum of this vertex and this vertex. And for every other is the same. And fy means the sum of the weights of this vertex, of this and this vertex. Okay? So now, if you write the product, you write a polynomial, which is the product of these linear polynomials, then if you replace each variable by some numbers, so phi means that you assign values to the variables, you plug into the polynomial, and then the polynomial is non-zero if and only if this phi is a proper edge weighting. So the problem of finding proper edge weighting became finding what they call non-zero points of the polynomial. Non-zero points of the polynomial. So this is a polynomial in general for general graph, and you want to find the assignment, which is a proper edge weighting. That means to find the non-zero points of this polynomial. Now the computational understandings give a sufficient condition for finding, so that for the existence of non-zero point in a grade. So the computational understandings says that if you write your polynomial as a summation of monomials, if there's one monomial of highest degree, which is a non-zero coefficient, so this is a monomial of highest degree with non-zero coefficient, and then you give each variable a set of choices. How many choices you give to it the exponent plus 1. If you give each variable that many choices, then you can find the non-zero point of the polynomial in the grade, among the choices. So that's denoted by monomial P, the set of monomials of P with non-zero coefficients. And so we look at this polynomial. This is a polynomial of the graph we written before, and if this is monomial with non-zero coefficients, which is of highest degree because this polynomial is homogeneous. Every monomial is of highest degree. And if L is the least of the edges, for each edge, the number of permissible weights for this edge is the exponent here plus 1. Then you can find the proper edge weighting from this list. Now, what we want to do, we're going to prove that we can use this condition. We say this is enough. We can find a monomial. We can find a monomial with non-zero coefficient such that the exponent of each variable is at most 4. Right? Then if you give each variable 5 choices, then you can find a non-zero point. So that is the goal. Okay, that is the goal. Okay, so to use this combinatorial standards, what you need to do, you need to find a monomial of non-zero coefficient. Okay? Non-zero coefficient. And this monomial, each variable has to be raised to the power at most 4. Okay? So how do you calculate the coefficient of a monomial? Okay? So let's look at this example. So you write it as a linear combination of monomials, and there's a monomial which is because this degree is 5, right? This is one of the monomial. This is one of the monomial. This is another monomial. What are the coefficient? What are the coefficient? How do you calculate? How do you find the coefficient of this monomial? Okay. So now you multiply this out. So what you need to do to multiply this out, you're going to choose one from these entries into multiplication. Choose one from each of these and multiply it together. You get a monomial. And then, okay, I write this polynomial in this form as a matrix. So these are the coefficients of the products of each linear term. And what you're going to do, you're going to find for each. So for each row, you're going to choose one column. You choose one entry. You're going to choose one entry from each row into the multiplication. Right? That means choose one to multiply it. And to make sure that X, Y, Z, W, T each has power 1. Power 1, that means you're going to choose exactly once from the first column, second column, and so on. Because each time you choose from that column, the corresponding variable, the powers increased by 1. Right? Because you choose the first column, that means X is going to enter into multiplication. So now, because I want each variable to have is raised to the power to 1, and therefore I'm going to choose from each column once. So that is I'm going to choose from each row, each column exactly once, okay? And then I multiply them together and take summation. That is the coefficient. So I have this matrix. What I'm doing is just find the parent of this matrix. That means you take each column, you take one entry from each row and each column and multiply them and then take the summation, which is the permanent of this matrix, which is very much like the determinant, but without this sign. That's the sign of the permutation. Okay. So then, how about the coefficient of this one? For this one, I'm going to choose twice from the first column, right? Because x is raised to the power 2. I'm not going to choose from this column because this column corresponds to t. T is raised to the power 0. So I'm not going to choose from this column. So what I need to choose twice from the first column, once from the second, once from the third, once from the fourth, and 0 from the fifth column. And that is what I'm going to do, to choose. Now, instead of choosing twice from the first column, what I do, I replace this. I put twice. I put the first column twice into the matrix. Okay? And instead of putting the last column there, I just delete it because it's not chosen. Right? So I get this matrix. Now I find the permanent of this matrix. Then I choose from each column and each row and each column again exactly once and take summation. But this choice is counted twice. Because I choose twice from the first column, now become choose once from this column, once from this column. It's double counted, right? Because there's permutation of the first time you choose from the first one, the second time choose the last one, and so on. So you divide it by 2. So then in general, suppose now let's first start with a matrix, a defined polynomial. Yes, because our matrix actually is defined by a matrix. Now, starting from an arbitrary matrix, I define polynomial in this way. Then I calculate. So our matrix is those form, and these are the coefficients. Right? So this is the matrix. Write down the. Then I look at the coefficient. I define the polynomial. Associated to this matrix, and I want to find out the coefficient of this monomial. So k is a vector, x is also a vector. This means x1 to the power k1 and so on, okay, times x2 to the power k2. And then the argument shows that the coefficient of this monomial in this polynomial is actually the permanent of this matrix. What is this matrix? This matrix is obtained from A by taking ki copies of the ith column. Okay? Because you're going to choose ki times from that column. Now instead of choosing ki times from that column, I simply put ki copies of that column in the matrix. Then I choose once from each row and each column. Okay? Then I get that's permanent of the matrix. But again, there's a double counting. Then there's a multiple counted, so I should divide it. So this is divide this. This is each choice counted this many times, and this is this notation. So this is the way to calculate the coefficient of this matrix. Now then, so the calculation of the coefficient of the polynomial, of the monomial of the polynomial, becomes the calculation of the permanent of this matrix, of some matrix. Okay. So now, so this is the matrix, and we're going to calculate the coefficient of this monomial, of given monomial in this matrix. But what is the what is the goal here? We want to find such a coefficient, such a monomial. So ki is each ki is at most 4, and the coefficient is non-zero. That's what we want to do. And the conjecture says that actually we're going to prove 4 is enough, but the conjecture the value is 2. So 2 is enough. So you can find such a monomial that each variable is raised to the power at most 2, and this coefficient non-zero. And if that conjecture is true, then of course the least version of 3 conjecture is true. Okay. And that conjecture is this one. So this is conjecture. This conjecture is related to some other conjectures about permanent of matrices. So I'm going to skip. But so it's somehow it's a conjecture motivated by this 1, 2, 3 conjecture, but it's related to some other conjectures about the permanent of matrices. So there may be some mysterious connection, and those the other conjectures are motivated by some other problems. So this 1, 2, 3 conjecture seems to be just it's interesting just because the statement is beautiful and it's difficult. So, but maybe there's something behind it. We don't know. So that's the reason that at least some other conjecture related to it. Okay, so it could be, but we don't know yet. Okay. Anyway, so now the problem is we can calculate the permanent of this matrix. Now it is NP hard to calculate the permanent of matrices. It's unlike the calculation of determinants. Determinants easy to calculate. You have this Gaussian elimination, but you don't have that anymore. So it's NP hard. So it's a difficult problem. We start with a difficult problem, we changed it, but to another difficult problem. Okay. So what are we going to do? We're going to this is for arbitrary matrix, right? But our matrix is not an arbitrary matrix. It's derived from the graph. So we're going to look into the structure of the graph, how the graph structure can be used to say our matrix is special. It has some special property that is useful. Okay, so then I define 2 other matrices. One is this is the kind is the instance matrix between the edges and the vertices. Okay, so that's before that start. That's what is special about this matrix. One feature of this matrix, of the previous matrix, is that the columns are not independent. In general, of course. Some case. Why is that? Because because you're going to take the summation of the edges around each vertex, right? Those, if you have every column can be expressed as a linear combination of those vectors. So the rank of that matrix is not the number of edges, it's the number of vertices. If you know if you write for each vertex, you write the summation of the variables incident to that vertex. That is a linear term. Every column is a difference of such a vector. So it's not a full rank matrix. So if you have many edges, then the rank is much less than the size. Okay. So this shows how to exploit that property. So I write one polynomial, one matrix, which is the incident matrix, but the incident matrix of a oriented graph. You put the direction of this on each edge, right? Because each edge have 2 end vertices. One is 1, the other end is -1. And then there's another matrix which is B, which is exactly instance matrix. Then you can say that your matrix CG, this is the matrix we're looking for. CG is actually AG times BG, the transpose of BG. Okay. So this tells you that the rank is the most H is the column is the number of vertices. And if you take CGK, so we are going to want to calculate the permanent of such a matrix. Right? And this is actually AG, BG, this K to the transpose. This is different. This is a square bracket. Square bracket means that instead of, so you put Ki copies of row of the ith row instead of column. This is column, this is row. Put the Ki times of the ith row into the matrix. And this is the so now instead of calculating instead of the original matrix, we're calculating the permanent of the product of two matrices. And now so again, how to calculate the permanent of this of such a matrix? Now instead of considering such a matrix, we go to the complex field. So we consider two arbitrary matrices. Now instead AG transpose, I take the AB, the conjugate transpose of this matrix. Okay, so this now the entries of A and B are complex numbers. And then so of course eventually we're going to return to real numbers, and this conjugate transpose is just transpose. Okay, that's transpose.
Can you remind me the definition of BG?
BG is just the incidence matrix. See, it's the instance of the matrix. So the rows are indexed by edges and columns indexed by vertices. And the H is also instance matrix, but now these edges are directed. So the 1 and minus 1. And then, so now we're going to calculate the permanent of the matrix, of the product of two matrices, A times the conjugate transpose of B. And then you write in this form through some calculation, just easy manipulation of this column, of these calculations. You say that, okay, let's forget about this calculation, just look at the final conclusion. The permanent of this matrix, is going to be, you look at this polynomial, so this is a polynomial, right? And you look at the coefficient of this monomial in this coefficient, in this matrix, and take the coefficient, and take the coefficient of this monomial in this matrix. This case, all the k's, you take all the k's, and then you take the summation of this. That is the permanent of this matrix. That is the permanent of this matrix. Okay, now I define given two polynomials. So you say that we go back. So we're looking at somehow this coefficient is related to polynomials, right? This is two other polynomials. Okay? So we define the inner product of two polynomials in this way. So the polynomial space is a vector space. Right? The monomials are the basis, and you just this is just the coordinate of this. This is a base of the matrix of the vector space. Right? This is the coordinates of these vectors. And you take define the inner product of two polynomials in this way. And this is very much like the inner product in our Euclidean space, but there's a weight in front. If you remove this, that is exactly the inner product of Euclidean space, right? Coordinate product and take summation of all the corresponding product of coordinates. Okay, but it's still an inner product. Okay, now so what we have shown is that we want to calculate the coefficient of some monomial, and that monomial, that coefficient is the parent of some matrix, and that parent of the matrix is the product of two polynomials. Okay, two polynomials. What are the polynomials we are looking for? What are the polynomials? We go back to look at what are the polynomials. The polynomials are these. Okay, one is let's look at again. What are the polynomials? One is FA, right? Remember that A is the instance matrix of the oriented graph, each direction, and FB. Now B is not just the instance matrix because we're going to put ki rows of the ith row into the matrix because we're going to. B is not the original, not original B. It's a B K. B square root K. Right? So then, what are the matrix? What are the polynomial now? Right, I'm taking the product of these two polynomials. One is so this one is just A, Fa. Right? Fa is of this form. Right? Fa is fixed. But FB, there's a K here. There's a K here. Right? K is the number of times you choose that that row. Each row is an age. How many times you choose that age? Right? And then you're going to put, so you put this age, for each age you have this term, but you put that age that many times into the matrix. So these are the two. So we're going to find the product of these two polynomials. So these two polynomials, in some sense, they are simpler than the original polynomial. Okay? They are simpler. And okay, so that's what that's what we want. So this is coefficient. We're given this k, and we want to find the product of it. This is the coefficient. This is not coefficient, but divided by some constant. Okay? So we just want the coefficients non-zero. Okay, so now we want to find. So you see that this one is fixed. This is A, but this one we're going to find this K, right? K is we're going to look for. K is going to the exponent. We don't know yet what are the KE for each age. We just want to prove. We don't need to find it out. We just need to. There is one K such that the KE is less or equal to 4. Of course, you can prove less or equal to 2. That will be better. Okay. So now we're going to prove less or equal to 4, so that the product is non-zero. But we don't know what is the K. Okay. Now, instead of finding a particular K, we're going to search in a subspace the generated by all those. So each polynomial is a vector, right? Generated by those vectors that we are looking for. We want it. So what are those vectors? Those vectors, those polynomials that have correspond to this K is less or equal to 4 for every age. So we just need to find the one that is one polynomial in the space, subspace, generated by those vectors, by those polynomials. Okay. And to find such a polynomial. Okay, so what then we want to say, okay, what kind of polynomial are you looking for? What kind of polynomial are you looking for? Okay. Those polynomials are the linear combination of those monomials h to the power k, ke is less or equal to 4. That's linear combination. What does that mean? That means that you're looking for polynomial of this form. F is of this form. Remember that you look at this QE to the it's always this xi plus xj. For each age, you're going to multiply those things, right? But then you're looking not just you just don't put age there. You put the linear combination of the ages there, okay, and then you multiply it. Then that is one polynomial in your subspace. Okay, so looking for those things. What I want to find the polynomial of this form. This coefficient arbitrary. You can choose whatever coefficient you choose, put there. But I want the number of times each age. So this is an age. Each age show up at most ke times in these linear combinations. If you can find such a polynomial, and then that is you can prove that you can find such a polynomial, and the product with this QE is non-zero, then you are done. Okay, so there are two problems now. One is find such a polynomial. Right? The other one is to prove the product is non-zero with this QE. Both problems, of course, these two problems are related, right? You find one, you cannot prove it, there's no use, then use. Right? So to prove that if you find, so if you guess, say one polynomial, say this must be the one, but still it's difficult to prove the product is non-zero. Okay? So the difficulty is, I think, is that we don't know how to prove the product of two polynomials is non-zero. It's very difficult. So it happens that in some special case, we have some way to do it. That's how we can prove some partial results, not the full conjecture. And if you find some other ways you can prove the product of two polynomials is non-zero, then that would be very helpful. Okay, let's look at one special case. How can you prove something like this? Okay, so we're looking for polynomial of this form, right? This form. Okay. We want to find such a one, which is non-zero product with QE. QE is, say, if G is triangle, QE is vertices 1, 2, 3, and this is QE. This is QE. Now, if you can find QE, if QE can be expressed in that form, then what you're doing, you find product QE and QE, then of course that is non-zero, right? That is long of this vector is non-zero because it's not a zero vector. This is one way to prove that the product of two polynomials is non-zero. I find QE there. Okay, that would be very good. Can you do it? In some cases I can do it. For example, triangle I can do it. Say triangle that I prove, and this is where I write QE in that form, in this form. I write QE in this form. Okay, you can see that. See, this is QE, and this is age minus this age. Age minus this age. This gives me this term. This gives me this term. This gives me this term. But this is another expression. This expression shows that QE is in the subspace generated by what I wanted. Actually, each age just appeared twice in this expression, right? So that means QE is there, and of course, then QE times QE is non-zero. Okay? And using this. Okay, so this is what I said. If you can find QE there, and you're done. And if you QE, if your QE each age is used at most twice, then you prove that the graph is at least reducible. And this is how we can prove some example like this. So if G is a graph, it decomposes into complete graphs of odd order, then I can find QE in that space where KE is at most 2. And therefore, those graphs are age-weight reducible, right? Because KE is at most 2.
What do you mean by decomposes? You mean the disjunct union of the...
Yeah, the ages the edges decompose. I mean the edges are the union, disjoint union of the edges that will be complete graphs.
You can have two complete graphs sharing about this.
Vertex, yeah, vertex is okay. You can share vertex, edge decomposition. Edge decomposition. And of course, every graph, for any connected non-bipartite graph, you can prove that QE is there, but now this KE is very large. KE is large, but then it's too large, therefore the result is not, it's much worse than what we know, so it's useless. Okay, so now for the result we want to prove. So the result for some special graph, if the edges can be decomposed into something, but not every graph can do that, right? So for the general graph, what do we do? We first find a good subset of the vertex set. So this J is good. It's a good subset. And once you find this subset, the edges are partitioned into 4 parts. Say this is the edges in this side. This EJ1 are those edges that are non-isolated edges. EJ2, that is edges in this side, are isolated edges on this side. And EJ3 are the edges between them. And EJ4 are the edges in this side. So you find such a partition, and then you get partition of the edges, and then you can write your QE as QEJ1 times QEJ2 times QJ times KJ4. So this is once you find the partition of the vertex in this way, you can express your QE as the product of 4 polynomials. And then based on these 4 polynomials, we're going to find a polynomial f. We're going to construct the f, which is again the product of 4 polynomials. And how do you construct these polynomials? F1 is obtained by induction hypothesis, and this QEJ in F1 is non-zero because that you can find by. So we're going induction, right? We're going to smaller graphs. The statement is true for smaller graphs, so we can find F1 for this subgraph. And F2, F3, F4 are constructed by using nice properties of good sets. Okay, because I said choose a good set, but I haven't said what is good, because the goodness is there's almost a full page of the properties, and if I put there, you cannot read it, and I cannot explain clearly. So just some set you can construct use these good properties. You can construct this F2, F3, F4, and so that the following code. Okay, so we're going to look at the product of this one. This product, of course, is this polynomial and this polynomial. And this good property says that I can separate this, I can pull out this one and this one, and the remaining 2 is the product of, so kind of simplify the product. And this one is non-zero by induction hypothesis, and this one is non-zero, which is kind of trivial. And then you want to prove that this one is non-zero. Okay, so I guess it doesn't make much sense to go to detail because I haven't said how to construct them. So anyway, I just show you so the what is used in the complex field. Right? So this. Anyway, so these polynomials, they have some special properties. They show you what is used for the complex numbers. Why we go to complex field? Okay, so it turns out that we are going to need to prove some. This is a very special polynomial, and we want to prove this is non-zero, and we want to prove this is non-zero. Then it turns out that it is enough to prove that this is a polynomial. This for any non-zero polynomial here, and the product is non-zero. But this again, this is a different inner product of polynomials. This is different. This is actually the Euclidean, the product, the inner product in Euclidean place. So this is the inner product of two polynomials. So there are two different inner product. So this one is just the summation of the product of the coordinates, and this is, there's a weight here. This is the one we used before. This is new one. This is this one. Okay. Somehow we change this to this one, right? Because there's the difference is just the coefficient is different. Right? You can feel that there should be some relation between these two products, but the details cause some calculations. Okay, so then so we end up, we want to prove something like this, and this is how this complex numbers is helpful, and this product can be written this way. This product you can decide this way, and then you plug in those special polynomials there, and you find out that you just integrate in some non-zero polynomials, non-zero functions, and each of them is non-negative. Okay? So you're integrating some function which is non-negative and which is non-zero. Then of course it's a continuous function. Of course the integration is positive, right? So it's non-zero. So that's how the complex numbers are used there. So anyway, this I guess just give you a feeling of how it is done. But I think the difficult part is that you guess two polynomials and how to prove that the inner product is non-zero. This we don't know how to do it. This is what is done here is that we find some very special polynomials, and then you can prove that the inner product is non-zero. In general, it seems that it should be many polynomials. The product should be non-zero. But we don't know how to prove that. So that is the difficult part. Okay, this is something I didn't. Okay, so there's one more conjecture open here. So that is, you see, every graph is K2 choosable. This is still open. So 2, that means each edge has 2 choices, and each vertex you can have many choices. That's also open. Okay, anyway. Okay, thank you.
Any questions? So does this proof also imply that you can assign your list can be chosen from the complex numbers instead of real?
Yeah. A list can be chosen from complex numbers.
I have a minor question. Maybe I missed one part. In applying the Stone-Sas, do we need to show the term that defines the leading one?
So the term is any term which is highest degree, leading, yes. But for this polynomials, it is a homogeneous polynomial. So every term is a leading term. It's highest degree.
Have you done some symbolic calculation to check the small cases?
No. I Actually, I don't know how to use the computer to help me to do some experiment.
Can we compute the lower bound of this number of the proper 3H weights?
So the lower bound is 3 is best possible.
What I mean is the number of these proper 3 weights.
The number of how many different ways you can assign weights for that.
Is it exponential?
Yeah, that is a good question. We haven't thought about that, but there's also a theorem of combinatorial Stanislas, the generalization of combinatorial Stanislas. So if you given this polynomial and you give these choices, you can find not just one, you can find many. So that is there's a theorem says that, but I haven't considered this particular problem by using that theorem. So you can, for example, if you look at reproducibility of planar graphs, okay, and then you can use combinatorial Einstein to prove it, and the result of the say is that okay, not just find one, you can find the exponentially many good least count. For this one, I guess it's also maybe it should be also if in particular if you have say for example you have 4 choices, maybe it should also be exponentially many. But I haven't looked at that problem. It's a good question.
Any other questions? Okay, if not, let's thank the speaker.